Here we are at example 3 from our 5.2 number 2 set of notes. We're asked to evaluate using synthetic substitution. Well, we see our polynomial, and we're trying to throw in -2 into that function. So as always, we take what we're trying to throw inside there and put him in that box. And then we drop down the coefficients. So 2, 2, 3, and -5. Now, if you had written this, such as this, you would actually end up not with the correct value in the end. And the reason for that is it is critical that you have all of the items going down the order in terms of the degree. So for example, what I mean by that is, notice we're starting off with this polynomial as x to the 4th, but then it jumps down to x squared. Believe it or not though, there still is an x cubed in between these. He's hidden, but he is there. Now the coefficient though, for that x cubed, actually comes out to be 0. Because 0 times anything, including x cubed, gives you 0, so you're not really then changing your original function, this polynomial. But when you're trying to do the synthetic substitution, the 0 is absolutely critical in having it such that you get the correct final result. Okay, so you have to make sure that you're going down the line with all of the appropriate coefficients. It's one of the very common mistakes when you're trying to do synthetic substitution. Believe me, when it comes to like the chapter test, that's definitely something that's going to be on there, just to see if you're paying attention, to see if you can recognize that. All right. So after that, we leave ourselves some space, draw the bar, and then the first item we always drop down. So in this case, the 2. Always multiplying with what's underneath our bar with what's inside the box. So -2 times +2 gives us -4. 0 minus 4 gives us -4. And again, just repeat the exact same process. -2 times -4 gives us +8. Add going down. Should have drawn the arrow. Adding going down, we end up with 2 plus 8 gives us 10. Multiplying again, we end up with -20. Adding going down, we end up with -17. Multiplying -2 times -17, we get +34. Add going down, we get 29. So then P of -2, when we threw -2 into the function, we would end up with a y value of 29. And so you might be asking yourself, well, Mr. B, why wouldn't you just throw -2 into the function and just see what it basically spits out? And that's very, very valuable in knowing, but when we start getting into synthetic division, we'll definitely see why synthetic substitution, pretty much the same method, is very, very handy. So right now it kind of seems trivial, like why would we do this? But it's kind of leading the way for synthetic division, which again is virtually the same thing as the synthetic substitution. Now, when we're talking really about, we didn't really talk about like the why this works, so that's something I would like to discuss. Let's start off with, maybe we have some polynomial. I wanted you guys to get a little more familiar with how synthetic substitution works before I kind of just jumped in there. But let's say we have some function, and we're going to throw in some value. We'll call this f of, let's see here, I want to use a. We'll go with f of t. F of t. And we're, again, throwing t inside the function anywhere that there is going to be an x. So usually we were kind of given like a number here, but in this case we're going to go with t. Let's say our function is we'll just start off with like a quadratic. So ax squared plus bx plus c. So again, that's just a quadratic in standard form. We've seen that in the past. And you want to use synthetic substitution along with that and kind of verify why it works. Well, again, t represents just some number that we would throw in that box. So t is going in the box. We drop down our coefficients, so a, b, and c. we draw the bar. And for the first one, we always just kind of bring down. So in this case, he's A. Well, again, with what's inside of our box, we are going to multiply it with what's underneath our bar. So in this case, we end up with AT. And like always, with synthetic substitution, we always just added going down. So in this case, because it has a T and it has A, and you're trying to add B to it, they're not really like terms. You know, when we actually did synthetic substitution, they were just numbers, so you were able to just add them together. But in this case, it's a little bit more difficult because you have just a bunch of different variables. So as a result, we end up then with AT plus B, though. That's how we can represent him. Next, again, we have something in our box. We're going to multiply with what's underneath our bar. So we have T times AT plus B. Over to the right, we'll just jot that down. T times AT plus B. Well, if you go ahead and distribute that, we end up with AT squared plus BT. So we have AT squared, just the T's being squared, plus BT. And like always, we just add going down. We end up then with AT squared plus BT plus C. Now notice this last piece, AT squared plus BT plus C. That's literally the same exact thing as if you were to take T from originally and throw him in for X, anywhere that there is that X. So this is kind of the verification as to why synthetic substitution actually works. And again, we really cared about f of t, what this last part was. And so that's again why synthetic substitution. Now again, I didn't want to throw that out from the start because this would have been pretty confusing, so that's why I wanted to get a few examples under our belt before we actually talk about kind of the short proof on behind why. And this works for any polynomial as well. You know, x to the third, x to the fourth, x to the fifth, and so on. But again, though, that is example 3 from our 5.2 number 2 set of notes.